Now let's direct our attention to the two main types of metabolic acidosis: anion gap metabolic acidosis, AGMA, and normal anion gap metabolic acidosis, and what causes them. In a metabolic acidosis, the primary problem is a drop in bicarbonate, either because we're losing it, as in a non-anion gap metabolic acidosis, or because it's being consumed during acid buffering, which is an anion gap metabolic acidosis. First up, let's discuss anion gap metabolic acidosis. The anion gap helps us identify whether unmeasured acids are accumulating. To understand this concept, we must first recognize that in normal circumstances, the serum cation concentration is roughly equal to the serum anion concentration. However, because there are anions not readily measured in our typical serologic testing, if we were to sum up our total anions and total cations, we would notice there is a difference between the values. The difference between these values is termed the anion gap, which is represented by the following equation. Ag is equal to sodium minus the sum of chloride and bicarbonate concentrations. A normal anion gap range is around 8 to 12 milliequivalents per liter, depending on the lab. In an anion gap metabolic acidosis, acids like lactic acid, keto acids, or toxins accumulate. The systemic bicarbonate is consumed, buffering the hydrogen ion, while the acids dissociate, leaving the accompanying anion behind. Therefore, the loss in bicarbonate is equal to the gain in anions, thereby increasing the anion gap. This results in an anion gap that exceeds the normal range previously discussed. Common causes of anion gap metabolic acidosis are often remembered with the modern GOLDMARK mnemonic. Let's go through these together. G stands for glycols, like ethylene glycol or propylene glycol. O stands for oxoproline, reflective of chronic acetaminophen use. L for L-lactate, lactic acidosis typically related to shock or hypoxia. D for D-lactate, which can be found in short bowel syndrome. M for methanol. A for aspirin, also referred to as salicylates. R for renal failure, which is reflected by reduced clearance of organic toxins. And K for keto acid or ketoacidosis, typically from diabetes, alcohol, or starvation. Clinically, an anion gap metabolic acidosis suggests there's an acid production or retention issue. Think hypoperfusion, sepsis, renal failure, or toxic ingestion. Now let's discuss a normal anion gap metabolic acidosis, also known as a hyperchloremic acidosis. The problem here isn't accumulation of unmeasured acids. It's related to bicarbonate loss, which often goes along with failure of acid excretion. Here, bicarbonate is still low, but the drop is balanced by a rise in chloride, maintaining electroneutrality and keeping the anion gap normal. Hence the hyperchloremic acidosis terminology. Now let's go through the causes of a non-anion gap metabolic acidosis. This is best remembered with the mnemonic HARDUP. So H is reflective of either hyperalimentation or hyperchloremia. A is reflective of acetazolamide, a carbonic anhydrase inhibitor, but don't forget about topiramate, which also does this. Both of these cause a type 1 and type 2 RTA. R is a renal tubular acidosis. D, U, and P are all forms of loss of bicarb-rich intestinal fluid. D stands for diarrhea. U stands for ureteral diversion or ileal loops. And P stands for a pancreatic fistula. Mechanistically, in GI losses, you're literally dumping bicarb out of the body. In a renal tubular acidosis, the kidney either fails to reabsorb bicarbonate or fails to secrete hydrogen to generate bicarbonate. Ultimately, the anion gap gives us a window into what type of acid-base disturbance is occurring and why. A non-anion gap metabolic acidosis is reflective of bicarbonate loss or renal acid retention. An anion gap metabolic acidosis is reflective of acid accumulation. Recognizing these patterns helps clinicians quickly move from a number to a diagnosis to the right treatment.